I'm going to start recording and I'll wait for students to join. Hopefully you all got the message, the announcement that that everything's online today and didn't have to learn that by the grapevine. Or just not everything, just my class.
What's today's plan? Objective?
I'm going to go over the Hawaiian pronunciation and the pig homework because students are stuck on the Hawaiian pronunciation homework and I want to make sure that you guys get an introduction to the pig homework. Because I had a number of students who did not know where to go with that homework, which is the homework that gets issued tomorrow. I had a number of students last semester who did not know where to go with that homework. And as a result, they decided to cheat. So they looked at it, they were overwhelmed by how big it was, even though it was less of it being big and more of a step-by-step building to a large program. And so as a result, I want to go over that homework as well. I want to point people in the right direction so that they can have the best chances of success. Okay. So again, I'm just going to wait a little bit for people to trickle in since I only see 62 people here and I feel like there should definitely be more. I'm glad I didn't decide to come in today. I'm not sure. My wife and I are like 99% sure this is allergies, but I feel like trash today. And so I didn't want to take the risk of accidentally exposing anybody to anything if I was sick. I'll take a COVID test later today. Just to be sure. But, you know, it's just would have just been impolite and hypocritical and a lot for me to come in. So I'm sorry for having to, you know, just tell you, hey, class is going to be online. Yep, that's exactly right, John. All right. All right, so let's talk about the Hawaiian Pronunciation Lab. All right, I'm not going to go over it like from scratch. I'm going to assume that, let me go ahead and remove what I've gone over with some students. I'm not going to assume, let me go ahead and actually put it on the desktop. Hawaii. So I'm not going to assume you haven't seen it before. I'm going to assume that you've looked at the homework before. Okay. And if you haven't, pay attention as best you can and then, you know, go over it and then come back to this video, which I'll post online after we're done. So the main thing for this assignment is that we will be doing is that we need to use dictionaries. I mean, you don't have to, but as you're going to see, it becomes a lot easier. Okay. And the program basically is made up of 3 parts, I guess we could say. We have basically the most difficult part, which is translating, or rather which is basically pronouncing our word, which I'll just call it pronounce. I'm not referencing my document. Oh, right. I should totally share my screen. Here we go. New share everything. Okay. So here we go. We've got ourselves a, so right now I'm just going to define our functions. We want to pronounce some kind of word. One function we also need to do is also validate what our word is, right? So for this one, I always like my code to be able to run no matter what. So at any point, so pronounce, and what I'll do is I'll have an output is equal to this and return our output. That's going to be our answer, which is saying, hey, this is how we pronounce this word. That's what our output is gonna store. And as you can see, I can run it. It's not gonna do anything, but it's not gonna crash as well. Now, what I also do over here is I've got we've got 3 classes of basically things that we need to worry about when we're trying to pronounce stuff. We've got our consonants, right? Like H or W or K. I'm not going to put down all of them. I don't need to put down all of them since I'm just trying to get you on the right track, right? But these are our consonants, and they have a list. And I don't have a dictionary for the consonants because for instance, if we're trying to do, let's see, keiki. So for instance, the Hawaiian word keiki over here, that's one of the words I love to test when we're running a program. That should come out as K key, right? And what we see is that the Ks don't get changed at all. In fact, any consonant does not get changed at all. Make sense? So that's why we can just have a list for our consonants. For our vowels, we have, for our single vowels, we have a, e, e, and so on and so forth, right? For our single vowels, right? Vowels are for our single vowels where they basically have a single translation. A, e, e. Just so, for instance, over here, the I gets replaced with 2 E's, right? And then we have double vowels as well. And this is where we use our map. Basically, the idea here is that we can say, hey, give me the pronunciation for A. Okay, it's ah. Give me the pronunciation for I. It's E. Give me the pronunciation for E. It's E. Similarly, for our double vowels, we can say, give me the pronunciation of EI, and that will give me A. And AI will give me I, or whatever it's supposed to be. Okay, now the idea here, now what makes this program more complicated than most programs is that you can't just do like K key dot, you can't do this. You cannot do this. You cannot do word dot replace all the I's with double E's, because you'd be changing this to have multiple E's in it. You just can't, like, it just doesn't work like that. You can't use a function to just blindly go through and change everything all at once. You have to go through multiple things. So first off, let's talk about validate. Validate, I leave to you for the most part. That's not too bad, because what we need to do to validate the word is basically make sure that the characters in the word are all valid characters. And we can do that with a for loop. You say for letter in this word and make sure that each letter is one of the valid characters. And if it is not, just throw it at, you return false. And when we get to the end, we return true because it was able to pass all the checks. Similarly, there's a part of this program is that we have to loop it. Basically keep asking the user if they want to enter a word, then validate, right? And a validation loop would look something like this, right? We'll have a main function that basically you could have a main function, but the idea here is we could say input word, I'm getting ahead of myself, but the idea here is that you could say enter a Hawaiian I'm not sure how word. While not validate word. And you can basically do this to keep asking the user to put in a word. we don't want to do any inputs over here in our functions, because our functions we should be able to test atomically without any kind of user interaction. All right. But this kind of thing where we're asking stuff, that's stuff that you should have had a good handle on for lab 6. Okay. So what we're going to do here now is, so I said, okay, this isn't so bad. Doing a loop to get everything done isn't so bad. I'm not going to lie though, the pronunciation, if you don't think, if you don't see it, it can be a bit tricky. So because what I see most students try to do here is that they try to do a for loop. So that like for letter in word, because that's how we've been iterating through stuff the entire time, right? We've been iterating that. So you've been primed to think, hey, let me iterate through one letter at a time, but we can't, not successfully. Why? Because we have letter pairs. Because there's sometimes we have to read 2 at once, two in one iteration of our loop. And sometimes we just need to read a single letter, depending on whether we have a consonant or a vowel or 2 vowels. So we need to move through this manually. And the way we are going to do that is with a while loop. So this is the way it works. Okay. And this will and for those of you who are stuck, this is probably going to give you the push you need to get this done. Okay. So we're going to set index is equal to 0. Okay. So while, so what we're going to do is we're going to say while index is less than length of word. So going back to K key, and again, the pass there is just so because, again, I like to have everything syntactically correct at all times. Pass always gets removed when as we're working. So for K key, right? K key has the indexes 0, 1, 2, 3, 4, right? So while the length of the word, which is 5, so while index is less than length of the words, so if we increase index, it will go from 0, 1, 2, 3, 4. It won't get an index 5. And then here's the thing, we'll be moving index manually. So we've got 3 cases of what we need to look at. So we want, basically we might either be dealing with a consonant, a vowel, or a double vowel. And the double vowel is bigger. So we're going to take a look at that first. So what we're going to ask is if, so we're starting here, if this is a double vowel. So how do I get this? Okay. So if word index, and I'm going to use just slice notation, index plus 2. So it will give me 2 letters. It goes up to, but doesn't include index plus 2. So, or to figure out how long it is, you just simply take the end condition and subtract the beginning condition. And you'll end up with 2. So it's too long. So you look at that and you ask, hey, is that word in double vowels? And that's going to check if it's in our key, or if it's one of the keys. It's going to check if it's EI or AI or any one of the other ones like double O, right? Again, these aren't all of them. You're going to have to add them all yourself. But I didn't want to waste everybody's time by having, watch me, put in stuff. That's not useful here. This is useful. So while index is less than word, what we want to do at this point, if this is in double vowels, that means that this part that I'm looking at is a double vowel. It's not in this case. But so let's go ahead and ask the next thing. If, else if, because we don't want to trigger this twice. We want, it's only, these are all mutually exclusive conditions. If word index in vowels, and then our third condition is that if it's a consonant. I suppose there's one more condition, which is that what if it's an apostrophe? But you can handle that the same way as you did a consonant. Consonant. Let's look at each of these kind of cases. You might have to add more to this, by the way, but this is the kind of the bulk of it. So let's say we're at index 1 and I just read EI and I found that that was in double vowels, right? Everybody following this so far? Okay, so I read EI. It's in double vowels. So now what I want to do is that I want to get the pronunciation of the double vowel from the dictionary. Would it still work if we have single vowels and consonants in one dictionary? It would become tougher for a reason you see. So this is a slice. So if you are having trouble with this, you need to review your, I think, chapter 5 or 6, which talks about slices, which basically says, let me get a subsection of this, right? New. Yeah, so give me this, da, da, da. Okay, so here, right, word equals K key word. So if, for instance, if our index is 2, if I do word 2, which is index to index plus 2, it doesn't give me just one thing. It gives me the entire range. It gives me a slice of it. Index to index plus 2 gives me IK. Index 2 and index 3. It goes up to, but does not include index 4. Okay. So basically, this is how we get 2 things. Okay. So what we want to do is we want to get the pronunciation from the dictionary. Basically, this is our key. So we want to get the value from the dictionary. We want to add that value to the output, then add a dash to the output. Okay, because, right, if we've got a double vowel, right, if we do, so what we're, right, if we've got, if our output is currently K and we see an EI, then we're going to want to add A and then a dash at the end so that we can do, so that when we read K and I, we'll do that. Excellent question. Lincoln asks, won't the code return an error if the index is 4? And that's, it's actually an interesting quirk of Python, which is that slices don't care. If you're, as long as your start value is in range, index 3 up to index 6, so long as your slice, right, note that there's no index 6, it's 0, 1, 2, 3, 4. As long as your start index is in range, it will go up to and include the end. And if it can't include any more than that, it's just going to stop at the end. It's kind of got like a bumper, right? So you won't go out of bounds. So it's pretty nice. So we don't have to worry about the index going out of bounds there. All right. So what we need to do is that we got to get the pronunciation of the double vowel. We add it to the out. We get that pronunciation, add it here, add a dash. And then what we got to do is that we're going to do index is equal to index plus 2. Or another way to put that, index plus equals 2, because we just read 2 letters as opposed to 1 letter. So we read index 1, we just read E and I, we just read the I, we don't want to read it again. So we want to add 2, so we go to the second K. Make sense? Now, for the And now it works pretty much exactly the same for vowels, which is get the pronunciation of the vowel from the dictionary, add that value to the output, add a dash to the output, except we're only reading one thing at this point. So, right, if we were reading, if we were doing Hawaii, for instance, we want to read the A and do a ah. So we would want huh, and then we'd go on to the A, which would give us huh, ah, and then put in a dash. And now for the consonants, okay, for the consonants, we do pretty much the exact same thing. If it's in the consonants, just add that consonant to the output index plus equals 1. Now there's a couple of exceptions there that we need to think about, and we don't use a dash with the consonants. But there is an exception, I think, with the W's and the V's with the pronunciation, depending on like other letters preceding it, but you can do a slice in the other direction if you need to. Or you can grab an index in the other direction. But this is the block that will get you where you need to go. This is the block you should use. And so if you do this pronunciation, this will give you, if you do this, it will give you the pronunciation for the word. Any questions about this one? Because that's pretty much all I have to say about this subject right over here. Because if I give you any more, it becomes trivial.
So should we put the double, like the W conditions in the double vowel? Will that?
The W, so what is it, the condition? It's
like if it's an I or before it, or, you know, it's like a few conditions like that.
If an I is before a W or something?
Yeah, it like changes the thing. So basically it's a double,
yeah, you could do it I would do it as not as a double vowel, because your double vowels are something specific.
right.
It's an edge case. So I personally, the way I would approach it is that if I hit a W, if I hit a W at index, I would check if word index -1, if the thing to the left, the thing before, was an I, and then figure out if that was our and that would let me know. The only issue with that, of course, is that, like, again, you're looking at possibly going index out of bounds, but again, a way around that is to do a slice. Okay, but that's also something that you should worry about, like, at the very end. Once you get this working, it's not too much hard to get. It's not much harder to get it working in general. You could do the W before and after. Again, you could, or you could make a separate, another thing you could do is that you could make a separate dictionary for that and have that as another LF block in there. And that would certainly take care of that. There's a lot of ways to slice that cake, so to speak. Make sense?
Yes, thank you.
All right. So what we're going to do now is I'm going to give us an introduction to Monte Carlo approximations based off of and an introduction to our last big homework, which is the last big mandatory homework, I should say, because there will be another one, regular expressions, and that will either be an extra credit or I'll assign you it, but I'll also increase the number of labs I drop. So, you know, it gets to be a freebie or a place of grade, depending on how we're doing. So the last mandatory assignment is Monte Carlo, and my question, I always have a Monte Carlo. I don't I will discuss the extra credit, the due dates for those later on, but generally no. The Monte Carlo is always on the final exam. Monte Carlo approximations are always on the final exam because they are great for testing. Do you understand a lot? Accumulations, writing functions, randomness, that kind of thing. So what are Monte Carlo approximations anyway? This is the lab category, and there will be 6 quizzes, and I'll be dropping one of the quizzes. Okay. So let's go ahead and check out. So first off, what is Monte Carlo before we get into that? Now, it's actually very interesting. Now, Monte Carlo is one of those interesting things. It's like there's a very interesting existence of certain states. Monte Carlo is a city in the Principality of Monaco. And Monaco is not exactly big. Give me 1 second. I'm about to phase out. All right, let me know when I'm back. Am I back? Okay, great. I had to turn off my VPN because it doesn't agree with Google sometimes, or Google doesn't agree with it. Thank you right now. So Monaco, right? It's a micronation. It's outlined. I clicked on it, outlined in red. And just because Europe has a very interesting and long history. Yeah, nice. Yeah, I think it's Nice. But you've got a number of very interesting, like, little principalities that just kind of crop up and exist, right? Everybody knows about Luxembourg, right? Being a very tiny nation, as well as Liechtenstein being also a fairly small nation. You know, but you've also got other microstates, as they're called, which are countries of their own. Andorra is interesting. It's right between France and Spain. It is ruled by co-princes, one of it, which I believe is one of the co-princes is, I believe, whoever the current president of France is. Let me just double check that. Andorra. Yeah, it is headed by 2 co-princes, the Bishop of Urgell in Catalonia and the President of France. So if you ever wanted to become a prince, that is one way to do so, become the President of France. So it's one of those interesting things. And so there's a lot of nations, and they got to specialize in something. And Monaco is known for Monte Carlo and its Monte Carlo Casino. As we can see, this is a beautiful building right here, right? I mean, that's just lovely. It is lavish. I mean, that screams luxury and money. So, but it is a casino, and casinos are games of chance. Now, interesting note. All right. If you want an interesting history and readable history, if you want an interesting history, by the way, of the history of statistics, I would recommend the Drunkard's Walk, which is not that one. Is it the Drunkard's Walk? Not a novel. There's mathematical. Yeah, there we go. The Drunkard's Walk, How Randomness Rules Our Lives, from 2008. It talks about various things and our various cognitive biases about statistics, but it also talks about the history of statistics. And statistics used to be viewed as like not something a respectable mathematician would do. Because statistics, the only people who wanted to do statistics were gamblers. And gambling, well, that's just not something a gentleman should do, I guess. So basically statistics and history of statistics is deeply tied to the history of gambling. And you know, for some things it takes like a lot of math to figure out what the outcomes are. Like, okay, what are the chances that the next card drawn is going to be a king, right? It's dependent on a lot of variables, how many kings there already are, how many kings we've seen, right? It's part of the reason why we've got techniques like card counting and the like, which is not actually illegal, by the way. Card counting is not illegal, but casinos would most likely want you to believe so. But that being said, it is actually very hard to do. It's easy, but hard to do in the moment. It takes a lot of practice. So anyway, and so the idea of Monte Carlo approximations comes from basically a very easy way to deal with dealing with statistics. Broad class of computational algorithms that rely on repeated random sampling to obtain numerical results. And history, basically the idea here is that suppose you want to go to Monte Carlo and you want to learn what the odds for a game are or what your chances of winning are. But the game is a bit too complex for you to do and you're not really good at math. The idea here is that I'll just count the wins and loss ratio. That's it. Just going to count how many games are played and how often the person wins. That's it. And the idea here is that if I watch for long enough, if I get enough games, right, then there's no longer going to be the randomness of a winning streak or a losing streak, which those happen because of random chance. But if I look for long enough, those streaks will normalize out, they'll cancel out, and eventually I'll end up with the real statistics. That's it. Monte Carlo approximations sound, or Monte Carlo methods sound super scary and super advanced, but they're really not. It's just counting. In this video over here with the Carnival scam science, he calculates your odds of winning any of these carnival games just by watching how often people fail at these games. So the Pig Lab goes on to that, and there is a associated assignment that we'll work on, that if we have time we'll work on today, and if not, definitely on Tuesday. So your next one is so this next upcoming assignment is called Pig, and it's about a dice game, okay? And the idea behind the game is that it's a 2-player game. It's basically a mathematical game of chicken, okay? And all you need to play it is 1d6, which is a 6-sided die, a d6, 6-sided die. So for instance, this die over here has 6 sides, it's a cube, okay? And the idea here is that you have 2 players and you take turns. You roll the die until one of 2 things happens. You say you're done rolling the die for your turn, or you roll a 1. Okay. So if you say stop, I'm done rolling for the turn, you'd sum up all the rolls you made. So let's go ahead and just kind of show you that in idle for a second. Idle. Okay. So let me go ahead and import random. Import random. Random.rand int. Now this is inclusive on both endpoints. So 1 to 6. So 3. My score for the turn is now 3. And I can continue rolling. 1. Nope. My turn is done. My score goes to 0 for the turn if I roll 1. Okay. Now it's player 2's turn. And player 2, she rolls a 5 and a 2 and a 5. So she's up to 12 points now. A 5, a 2, and a 5. And she says she's done. So she banks those points. They can't be touched anymore. She can't lose them anymore. She's done with her turn. So see what I mean by it's a game of chicken? You're like, okay, I'm going to keep rolling. I want to keep rolling until I get to that 1. But the question is, what point should I stop? Should I keep going? Because it's my turn. I'm at 0. She's 12 points ahead of me now. Okay. 2, I'm still behind. 3. So I'm up to 5 points. I'll keep going. 4. Okay, I'm at 9 points. Maybe I can get ahead now. 6. Okay, so I was at 9, so now I'm at 15. You know what? I think I'm gonna go further. Go. Okay, so I was at 15, now I'm at 19. You know what? I'm gonna stop now. 19 sounds good, right? That's kind of the strategy and the appeal here. It's basically, it's a lot of this is randomness, but also you can feel like there's a strategy to it. Like, how far should I pull ahead of the opponent? When should I stop going? So everybody understand the rules for this? Everybody understand the rules? Now the goal of the game is to reach 100. The first person to win, the first person who gets to 100 wins. Okay, that makes sense to everybody? You want to get to, so first thing you're going to do is you're going to roll the die, and that the first thing your turn is going to be a roll no matter what, right? And then you're going to start getting the choice as to roll or hold. Okay. So what we're going to do, so now that we know the rules, because the rules are simple, is that we have 8 small programs that we're going to do. We're going to eventually build up to basically playing against the computer. And the computer is going to use a strategy, a very basic strategy. The strategy the computer is going to use is that the computer is going to try to get 20 points, is that he's going to keep rolling until he hits 20 points. Once he gets 20 points or more for that turn, he banks it. Make sense? So the computer, if the computer is going, it's going to go like this. So computer's turn, 6, 12, 6, 12, 17. It's really good rolls, 6, 12, so 23. So the computer just rolled 23. That's more than 20. So it stops, it holds, it banks it for the turn. That's the computer strategy. Computer's turn again. 4, 4, 6, 14 points, 19 points, 22 points. So the idea here is that the computer banks again. So it's going to keep going to hold. It's going to keep going until it can get 20 points. Make sense? That is the computer strategy. That is so eventually. So what we're going to be building up to is that we build up to the player playing against the computer and taking turns with the computer. So where does the Monte Carlo approximation come in this? Well, it comes in with smaller parts of the program. For instance, I want to know, like, during part 2, what we're going to do is we're going to simulate what the outcomes of this strategy are. And the idea is, like, I want to see how successful the strategy of hold at 20 is. How often do I go bust, so to speak? In other words, get 0 for the turn, versus how often do I succeed? And then question 3 is, what about a different strategy? What if I set it to be a different number? And, like, what if I want to just see what's my shots of going for broke, going to 0 to 100 in a single turn? And actually, the chances are a bit higher than you think. It's about 1%. There's a 1% chance that you could get 100 points in a single turn. So play 100 games of it. Take 100 turns and you might get there. Okay, so that's where the Monte Carlo comes in. But we're going to slowly build it up is kind of the idea. Part 4. So what is part 1? Part 1 is we are going to basically simulate this strategy, okay, for the computer. Just automatically roll, no input from the user, whatsoever. Basically, we're going to implement the computer strategy first for 1 turn. And what we're going to do is that we are going to roll the dice until the computer rolls a 1, or the computer gets to 20 and decides to hold. Make sense? Then we're going to simulate the outcomes of that. Then we're going to extend the strategy to try to change it. And then we're going to change it so that we can, at part 4, what we do is that we basically say, here's the current score. Show me how the score is affected now that we did our turn. And now this is basically, and then at 5, we basically do a single 1-player game of pig. Okay, so let's go ahead and get started on this. Okay, new file. Control S. And I will make sure to, share this with you all so you don't have to furiously try to copy this down, okay? I want you to try to follow along as best you can in understanding it, not necessarily typing it down. Okay, so first off, almost any time that we are dealing with Monte Carlo approximations, we are dealing with randomness, which necessitates importing the random library. Do not, under any circumstances, name a file random.py, because otherwise bad things will happen. Because if you try to import something that already a file that's built into Python, but you have a name that's conflicts with it, you're going to be in for a confusing time. So anyway, but this is good. I named it pig. That's fine. So import random. And now basically we are going to do our first part of the assignment, which is one automated pig, a turn of pig. So what I'm going to decide so it doesn't need, the user doesn't need to input anything here. So def, let's call it, I'm going to call it, I'll just call it part one or auto pig or something. Part one takes in no inputs. And rather than creating a bunch of files, I'll create a bunch of methods or functions so that I can copy that pretty easily and test them pretty easily. So the idea here is that I'm also going to write before I do this, I'm going to write the function that I'm going to be calling a lot, which is def roll D6. Now, a lot of time, one notation I will be using a lot is Dungeons and Dragons or just RPG style dice notation a lot, because dice come in more sides than just a 6-sided die. For instance, here's a 20-sided die, right? Here's a 10-sided die. I played a lot of Dungeons and Dragons and other kinds of tabletop RPGs when I get the chance. And the typical notation we do for stuff like this is that if you're rolling 2 6-sided die, we write that as 2d6. That just means 2 6-sided dice. The TU Gamers Guild, the Temple's Gamers Guild, which I am faculty advisor for, and they have a Discord. They do Dungeons and Dragons, I believe, sometimes. So keep that in mind. I might eventually start doing stuff, but it would feel really weird to do that with some I'd love to do it with current students, but it would also be really weird because then, that kind of, because if you do poorly in the class and I'm like, oh, what am I going to do now? They're my friend now. I can't fail my friends. So, but, so a lot of times, but I do play a lot of Dungeons and Dragons. My most recent campaign was I DM'd Curse of Strahd, and that was a lot of fun. My players were successfully able to clear it, because my players are incredible and creative. And then I'm currently playing Tomb of Annihilation as a fighter wizard, essentially. So I do play a lot of D&D. So anyway, so going on, 1d8 would mean 1 8-sided die. 3d8 means 3 8-sided die. So if you hear me refer to a D6, that's just saying 1 6-sided die. So when I'm saying roll D6 over here, I'm saying roll 1 6-sided die. And that's exactly what this function is going to, this is what this function is going to do. It's just going to return random dot rand int 1 to 6. That's it. That's all. That's how we simulate rolling a 6-sided die, right? Because a 6-sided die, the idea here is that every single outcome is equally likely, allegedly, right? The die could be like, could be a bit biased towards one side or another, but but it's statistically random. And here, again, the roll D6, that's statistically random. So part one, what we're going to do is we are going to say, so what we're trying to do is simulate a single turn. So we're going to say turn score is equal to 0. And then at the end, we are going to return the turn score. Make sense? Now, this is going to go through a lot of revision. So that's why I'm part of the reason I'm saying don't copy it necessarily, because I'll be putting in print statements and then I'll be removing those print statements at some point so that I can use it. So part one, turn score, which is, so here's, we've got our turn score, which is our 0. And so what we want to do is we want to roll our dice. So what I'm going to do is I'm going to say the result of our roll is equal to roll D6, right? We're going to roll that dice. Or let's go ahead and say why, rather than using, you know what, I'm going to do a while loop instead, because we don't know how many times we're going to need to roll this dice. So I'm going to create a condition called done. This is how I like to do while loops. Done is equal to false. We are not done. So while not done, we want to roll our D6, which calls the function we just wrote up here. And now we ask ourselves if it's a 1 or not. If result equals 1, then we need to do stuff. If it's not equal to 1, here's what we need to do. If it's not equal to 1, then we add that to our turn score. Turn score is equal to turn score plus the result. Right now, we're doing its turn score is equal to turn score plus a result. We aren't going to call roll D6. It's not turn score is equal to turn score plus roll D6, because that would give us a new random number. That's a common mistake, by the way. That would give us a new random number. So while not done, we go ahead and we get our result. If our result is 1, we're going to do that in a bit. If it's not 1, we add that to our turn score. And then the assignment says, hey, it's going to use our strategy. It's going to automatically roll our strategy where it only stops when their turn score is greater than or equal to 20. So if turn score is greater than or equal to 20, this is what makes why I like doing it like this. Then we just simply say, done is true, right? We're done. Okay, so what if we get a 1? Well, if it's a 1, we lose all our points for the turn. So we say turn score is equal to 0 and done is equal to true. Okay. Everybody following so far? So the idea here is that if I roll, I'll roll the dice and I'll stop only once we get a 1 or the total score gets above 20. And then when we're done, we return it. So let's go ahead and add in some print statements so we can see. So example output, roll. So print roll colon, we'll do a tab there, plus str. Actually, I don't need to do any of that. Roll, just comma, roll, result, boom. Yes, you can come up, Blazer. Roll. Then I'm talking to my students. This is just for the first player. We don't worry about a second player until like part 5 or 6, I believe. Guess laser. Turn score is equal to turn score. So here, what we see now is, now if I roll part 1, so if I call part 1 now, we'll get rolled 6, turn score 6, roll 2, see how it adds up. But I don't want it there. I want it here. Rolled 6 and 1. So we got a 0. Rolled a 3, a 5, a 2, a 4, a 2, a 2. So if we add those all up, 6 plus 10, and 6 plus 4, and 5 plus 5. So that's 2 10s. So it becomes, so it's 20. Roll it, roll it. So see how we're rolling it and it adds up those totals. Everybody follow this algorithm so far? So now the reason I have the return is because I like to be able to just simply, now that I know that it's working, I can comment it out. I can comment out these prints, which serve as a debug, and say, hey, just print the result over here. 0, 0, 20, 0, 0. A lot of zeros, right? 21 until not. Yeah, this is just for the first player or for the computer. We're not going to worry about the other stuff. So let's go ahead and now do part 2. Def part 2, which is, we want to see how successful this strategy is. Hold at 20 outcomes. Simulate a given number of hold at 20 turns and report the estimated probabilities of the scoring outcomes. All right. So enter a single positive integer indicating the number of terms to be simulated. I am working, Laser. If you want to play upstairs, you can be upstairs, but don't bother me. But please don't bother me, okay? So let's go ahead and do part 2. So it says we want the user to input the number of terms. So I'll always do my inputs outside of the function. So, and then pass the value, because doing user input I find to be annoying and it does that. So I'll just pass the number of turns I want to run into there. And then we can ask the user outside of the function how many turns they want. So basically what we're going to do is that we want to figure out the probability of the scoring outcomes. In other words, how often will I get a 0? How often do I get a 20, a 21, a 22, a 23, a 24, or 25? These are all the possible outcomes, right, of the hold at 20 strategy, right? Which is that I either don't get anything or I get 6 different outcomes, one for directly landing on it and then going over and above it. So how do I go about doing this? Enter a, so let's see. So, and the answer is, I'm going to count the number of outcomes. That's what Monte Carlo is. That's how I calculate the probabilities. Rolling 6-sided dice and calculating the conditions is a bit too much. So we're not going to calculate it. We're going to estimate it by simulating this a bunch of times. We're going to simulate this thing a bunch of times. So we're going to simulate it turns number of times. So what we're going to do is, essentially we are going to say, so essentially what I'm going to do is this, something like this. For in turns, sorry, in range turns, you know, except I'm not going to print out the scores, but what I'm going to do is I'm going to, so print out part 1. So if I do this, so what I'm going to do is basically I'm going to simulate this. Okay. I'm going to simulate part 1, however many times, probably not just 10 times, but like 100,000 times, like the input says. And what I'm going to do is I'm going to count up the amount of times I see this. So I got 1, 2, 3, 4, 5, 6 zeros, a 20, and 3 22s. So my statistics, my estimated probability is that we have a 60% chance of getting a 0, a 10% chance of getting a 20, and a 30% chance of getting a 22. Everybody see how that kind of, how that works? Right? So that, but those aren't the real, that's not really a great estimation because that implies we have a 0% chance of getting a 21, and that's obviously not true. Right? So no, you are not. You are getting Joshua, you are not calling the function, you're not calling part 1. That's what you're not doing. You got to actually invoke it over here like that. So what we're going to do is that we are going to count the outcomes using a dictionary. That's the way I like to do it. Okay. So, so what I'll do is I'll say outcomes is equal to, okay. And then I'll go ahead and populate our outcomes. Okay. Because that way outcome dot, so the outcome, we have 0 instances of 0, right? And then for, let's see, for score in range 20 to up to, but not including 26, outcomes 0, not 0, of that score, I've seen it happen 0 times so far. Everybody see what I've done here? I've basically, what I've done is that I have, I basically initialized all of these outcomes, all these possible scores to 0, right? So let me go ahead and again, just kind of run it. And this is why it's like super valuable to have your function, your code always be runnable. Part 2 turn. So 10. So there, right, you see we've seen 0 0 times, 20 0 times, 21 0 times, 22 0 times, 23 0 times, 24 0 times, and 25 0 times. That's exactly what we would like at the start. Make sense? Okay. So now, what do I want to do now? Well, the idea here is that we're going to run this. We're going to run part 1, however many times we say, and we're going to get the result from that, right? We're going to get the score from that. Score is equal to that, right? Turn score. Let's just call it turn score. Okay. So we get the turn score at the end of part 1. We could call it whatever we want. We could call it X or whatever, or outcome or whatever. But I'm going to call it turn score because that's what we get. And so now what we do is that we say, hey, outcomes of that turn score, sorry, outcomes of that turn score, which is either going to be a 0, a 21, a 22, a 23, a 24, or a 25. So in other words, something I've already initialized my dictionary with, so I don't have to check if it already is in there, is equal to, I'm going to add 1 to that. And now print And now I'm not done yet but I'm going to print out my outcomes. Right? So I've run it 10 times. I got 8 zeros, 123 and 124. Make sense? Is everybody following so far? That's a Monte Carlo approximation. Now let's change this. Let's go ahead and make this readable. Print score. Print score /t. And then probability. Okay. And then what we'll do is for score in outcomes, what we're going to do is that we are going to, so for each of the possible scores we can get, we will print out 2 things. The first is the score, right? And then let's go ahead. We'll go ahead and we'll do the next. We'll save the next part for after we do this because I want to take it a bit slower. Score outcomes of that score. So how many times I've seen this. So all I'm doing is I am just going to be printing this vertically. That's all that's changed. And let's go ahead and we need to, I want it to be tabbed. So I'm going to just cheat and do sep is equal to, so this is one of the things you can do to the print function, which is say, hey, when I have a comma, I want to separate it by spaces. I'd like to separate it by tabs. Looks cleaner now. Okay. Score probability. For zeros, 4 20s, and 2 25s. Excellent. But this is not the probability. This is the number of outcomes, right? The probability that it occurs is the number of times that outcome occurred divided by the number of times you've tried it. So in other words, since I did this 10 times, I should divide this by 10, right? So in that case, I'll just simply divide by the number of turns. And there we go. Probability 5, 2, 0, 2, 1, and 0. But this is just with 10 outcomes. But the idea here with Monte Carlo approximations, these outcomes, this estimation is bad. Again, a 0% chance of getting a 21. That doesn't really make sense. Same with the 25, especially when we had 2 occur last time. But the idea is that if we do more of these, this time I did 100, we start getting closer and closer to the real odds. Does that make sense? And so what we can see here is that we've got, and so now, and your computer can generate random numbers quickly, like there's no tomorrow. So that's 100,000 right there. And we see that basically we've got about a 62% chance of getting a 0 with this hold at 20 strategy. And then about 10% for 20 and 21, about 7.5 for 22, about 5% for 23. If we want this to be a bit more readable in terms of percentages, we can do that. We can do divide by, so we divide by the number of turns, then we can multiply by 100, and then turn that into a string, and then add a parentheses. And now it becomes a bit easier to read. So does that make sense to everybody? All right. So what about part 3? And this is going to be the last thing I think we do for the day. which is the hold at X outcomes, as the previous exercise, but allow the user to specify the hold value. And notice I didn't do the bit where it asked you. I assume that you know how to do that, so you will be doing that. Part 3, as the previous exercise, but allow the user to specify the hold value. Was the probability of reaching 100 in a single turn if you allow the CPU to hold at 100? So let's go ahead and rewrite part 1 for a second. For this part, because this seems useful. The idea here is that rather than holding at 20, right, we want the user to specify a hold value. Maybe the strategy is hold at 10. So try to get to 10 or more points, try to get to 20 or more points, or try to get to 50 or more points in a single turn. Make sense? So what I'm going to do is I'm going to write a new function, hold at X turn. And it will be a hold value. We're going to hold at this value. Make sense? So I'm going to pass in, rather than just passing in nothing, I'm going to pass in a value that we're going to hold at. And the only difference here is that instead of 20, I have a variable. So this function is exactly the same as part 1 if I pass in a 20. Make sense? See how it's exactly the same thing. If I pass in a 20, this whole value over here would become 20 over here. Make sense? So see how I just quickly rewrote that function. But now I can also do things like let 10. Try to get to 10 or more points now. And we'll see that I get a 0, because I'm unlucky, 14, 0, 10, 10, 10, 10, 0. So is that a better strategy? Let's find out. What are the chances of that? So part 3 is like part 2. Okay. Part 3 is pretty much like part 2, except we're going to be taking in 2 variables, the number of turns and the hold at and the hold value. Make sense? So we need to do a couple things to modify this, right? So let's read through it. So our first thing we did here was set up initialize our dictionary. And we initialized it this way. We initialized it because when we're printing out our outcomes, we want them to come out in a clean order, in the sorted order. And the only way to do that is by either sorting it at the end, which is a bit of a hassle, or initializing our keys at the beginning. And we can do that because we know what we want. In this case, it was in part 2, it was we wanted to start at 20 and then do 21, 22, 23, 24, 25, and the 0 at the beginning. But, okay, what about hold value? Well, let's say hold value is 10. So in this case, what I'm going to do is I'm going to replace 20 with hold value. That would be 10 up to, but not including 16, right? Makes sense? So all I've done is I've replaced the 20. I've replaced all instances of 20 with hold value. Instead of hold value, instead of 20 and 26, I have 20 and 20 plus 6, or hold value and hold value plus 6. Okay. And now instead of calling part 1, which was hold at, which was a, instead of part 1, okay, which was just hold at 20, I'm going to do hold at X turn. And to do that again, I want to do hold at X turn instead of part 1. And I need to put in the value that we're going to hold at. And that's it. We've done part 3, assuming we rename the function to actually be part 3 now. So now let's go ahead and call part 3 10 times on a hold value of 15. And we see that for 15, and we now see our score range is from 15 to 20. No longer is it 20 to 25. Make sense? All I did was change these literal values, these values that are set in stone, into variables. That makes it a lot more flexible. So let's go ahead and do, again, 100,000 outcomes. And we see that the probability of getting a 0, if I go with a lower number, is about 10. If I go 15 instead of 100, I go from 63, it's from a 62% chance of getting a 0 from nothing that turned to a 53% chance. If I go all the way down to 10, right? And then I only get a 40%. If I go down to 6, all the way down to 6 before I bank, makes sense. So this is part 3, where I've just changed part 2's variables over here. So I changed for this, all I did was I added this variable to part 2, this argument. So why is it hold value plus 6? And the reason is that we had 20 and we had 26, right? Because we wanted 20, 21, 22, 23, 24, 25. We wanted 6 values. 20, 21, 22, 23, 24, 25. That's 6 values, right? So it went up to, but did not include 26, because those are the possible outcomes when you're trying to get 20 or more, and only 20 or more. When you stop when you hit 20. So outcome. So now when we turn it into a variable, right, it's hold value. So this is the start of the hold value, and 20 is equal to just 20 plus, sorry, 26 is just equal to 20 plus 6. Hold value plus 6. So now the hold value is a variable, so we can get a different outcome. All right. And then what I changed over here from part 2 was, instead of calling part 1, I called the new function I called, which just had 2 changes to it, where I took in another variable and I replaced the 20 with that one. So now, finally, we can answer the question, what is the chance? What are the outcomes when I run 100? So if I'm trying to win the game outright without any points, then I have about a 1% chance of doing so. Right, and why 1%? Because these add up to a bit more than 1%. So those are the first 3 parts of your homework done. Now I'm going to save this, and I'm going to stop sharing for a second. Stop sharing. I'm going to go ahead and save this, and I'm going to send this out as an announcement. Okay. Code from, because that's the easiest way to get it to you all. All right. Attachment. Hawaii attachment pig. Although I know some of you may have issues getting that. Here is the code from class. I will also post it on, I'll also share it on Zoom. There we go. Let me go ahead and share it on Zoom as well. Send to everybody in the meeting, and there. Check your chat box. All right. So it's 3:15 and I think I did pretty good today. And I hope this really helps you get started with your work. Now what we'll do on next Tuesday is that we're going to go over what originally I had planned for today. And what that is that we want to look at the Monte Hall problem using Monte Carlo methods, Monte Hall being completely different than Monte Carlo. So if you would, so I recommend, if you want to get it, I recommend looking up via Wikipedia or well, there's a number of videos. The number file video I shared on Canvas about the Monte Hall problem, definitely watch that. Okay. Also, the Wikipedia article on the Monte Hall problem is very good. It's a statistical paradox. And be sure to watch this video for Monte Carlo approximation, this problem over here, this video over here. So we can understand what the big kind of thing we're going to do. We're also going to do simulation of pi, just like similar to how this is a simulation of pi over here in the second video. So watch those videos. Okay, but again, what is Monte Carlo? We are just simply watching we're just simply watching the outcomes. We're just simply running an experiment and we're saying math is hard. So I'm just going to simulate the game. I'm just going to simulate the game that's being played. So we're going to do that exercise on Thursday. No, I didn't import. I was waiting to get more responses for the quiz correction forms before I did that. And then I'll probably import it to Canvas this weekend. I've been feeling under the weather. I had like a terrible headache last night. So I got literally nothing done. On Thursday, what we are going to do is that we're going to start looking at scam games that look fair on the outside. But in fact, they are completely unfair games, games that give an advantage to the person who is proposing the game, and is a good way for an unscrupulous individual to basically, rake in some money. Yes, the merge is happening this upcoming weekend. I'm sorry for the delay in that. It's just been, again, I meant to get it earlier done, but stuff happened and then I got this. I'm like 99% sure it's allergies. But I also, again, it would be hypocritical for me to say, stay home if you're feeling sick, and then for me to come in while feeling sick and possibly expose you all to germs. All right, so my voice is basically at its limit at this point, so I will see you all next week, and I hope you have a great weekend.